Okay, let's just do a couple more standard examples of induction. We'll go into something a little bit more complicated after we've done these. Okay, so just a couple of standard examples. So let x be any real number larger than 1, then for all integers n, or for all natural numbers n, 1 plus x to the n is bigger than or equal to 1 plus nx. Okay, this is a fairly standard inequality result. So let's look at some scratch work. So because we're going to prove this by induction, we just break it up into the two usual steps. We look at the base case, so when n equals 1, we just have 1 plus x to the 1 is equal to 1 plus x. So everything's good there. We don't have anything to do. Now let's look at the induction step. So let's assume that the result holds for n equals k, so that 1 plus x to the k is bigger than or equal to 1 plus k times x. Well, now we can multiply both sides of this expression by 1 plus x to start to make this look like the inequality we want, because we want to show that 1 plus x to the k plus 1 is bigger than or equal to 1 plus k plus 1 x. So we can take this equality and multiply it by 1 plus x to get 1 plus x times this, which is exactly 1 plus x to the k plus 1, which we want. That's the inequality we're trying to show based on our assumption that p of k is true. Well, then let's expand the right-hand side of this. We know that this is bigger than or equal to 1 plus x times 1 plus kx. Okay, that's by our assumption that this inequality holds. And the right-hand side is 1 plus k plus 1x plus kx squared, just by expanding this out. Now, since x squared here is bigger than or equal to 0, and k is bigger than or equal to 1, we know this term here is bigger than or equal to 0, and so this whole expression here is bigger than the thing that we want. So 1 plus k plus 1x is bigger than or equal to 1 plus k plus 1x, okay? Which is exactly this expression that we're trying to show. Now, this all seems reasonable, but we should be thinking to ourselves, hold on, there's this extra condition here that x has to be bigger than or equal to minus 1, strictly bigger than minus 1. Where did we use that fact in this work? Because if we didn't use that fact, we should be a little bit suspicious. And where it actually shows up is here, when we multiply by 1 plus x. So when we've taken this expression and multiplied it by 1 plus x, we've left the inequality pointing in the same direction. Now that's true that this is bigger than this because we're definitely multiplying by something positive. In particular, we know that 1 plus x is bigger than 0. So when we multiply through by it, the inequality is conserved. On the other hand, if this thing were negative, then the inequality would flip. Okay? So we have used this fact that x is bigger than or equal to minus 1, but maybe we should alert the reader to it when we write things up nicely. So let's do that now. So, proof. We proceed by induction. So we're just warning the reader that we're going to use induction. Assume that x is bigger than or equal to, or strictly bigger than minus 1. Now, base case, so again, we're just alerting the reader to the structure of our proof here. When n equals 1, everything works. So that's good. Now, inductive step, let's assume the result holds for n equals k, so that that inequality holds. Then we're multiplying both sides of the inequality by 1 plus x, and that's fine because 1 plus x is bigger than 0. So we're just alerting the reader to this thing here that we kind of skipped over in our scratch work that we should be careful about. So we're just making sure the reader realizes, hey, there's something a little bit careful going on here. And then we just expand things out, and then since this term here is bigger than or equal to 0, we can just drop it and we get the inequality we want. So the result holds for n equals k plus 1. So when it holds for n equals k, then it holds for n equals k plus 1. So we've proved the inductive step. And so then by induction, it works for all natural numbers n, as we want. Okay? So this is a nice little result. It turns out to be quite useful. So let's do another example. So this is our first summation example. And so this is telling us that the sum of odd numbers is a square. So 1 plus 3 plus up to 2n minus 1 is n squared for all natural numbers n. Okay. So base case, we just stick in n equals 1. Well, this sum is just 1, which is 1 squared. So everything works when n equals 1. Now let's look at the inductive step. The inductive step, we assume that the result holds when n equals k. So we're just making sure here that we're assuming the result holds when n equals k. Now we need to get to the result when n equals k plus 1. So we want 1 plus 3 plus dot 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 plus 2k plus 1. Okay, so if we substitute n is k plus 1, that's what we're going to get. And we want this to be k plus 1 squared. So what we're going to try to do is try to take this line here and make it look like what we want. Because remember, we're actually proving that p of k implies p of k plus 1. So we take this result here, and I'm just going to add the next term to both sides, because adding this next term here makes this expression look like the expression we need when n equals k plus 1. Okay? And then, of course, I have to add the same thing to the other side, and we can see that this is just k plus 1 squared. So when p of k is true, so we assumed here p of k, and we get to p of k plus 1. So assuming p of k, we can get to p of k plus 1. I'm just writing on my face here, which I guess is bad form. Okay. Now, something to be careful of here. Don't think of this as just adding the next term to both sides. Induction is not just adding the next term. We're really proving that if we assume that it's true when n equals k, then it is true when n equals k plus 1. And the way that we can show that for this particular example is by adding the next term. But in general, that's not what induction is. So let's write it up nicely. So, proof. We prove the result by induction. So, when n equals 1, everything works out properly. Good. Inductive step, we assume that this holds. So, 1 plus 3 plus so forth up to 2k minus 1, that's k squared. But then, by adding the next term to both sides, we get the result that we want. So, p of k implies p of k plus 1. So the base case is true, and the inductive step is true, so the result holds for all natural numbers n by induction. Now we don't really need to say by induction up here and by induction down there, but it's not going to hurt us to put that there. This is telling the reader of the structure of the result, and this is telling the reader how everything wraps up together. Probably don't need both, but it's not going to hurt us by putting in those extra words. And again, I'm going to just harp on about this point here. The inductive step is not just adding the next term. We really are showing that if it's true for n equals k, then it's true for n equals k plus 1. That's how we should think of induction, even in these simple summation examples. Okay, and I think that's where I'm going to stop.